Good afternoon, everyone. I am Biswajit from Tata Institute of Fundamental Research. First of all, let me thank the organizers for organizing such a good conference and inviting me to present our work. I'm going to talk about simple quantum Hall effect in ABA trilayer graphene. And many of you might not know about our institute. This is our institute by the Arabian Sea, and this is our current group, and Professor Mandar Deshmukh is my supervisor. Okay, so let me start with the acknowledging our collaborators for theoretical support. We have collaborated with Professor Rajdeep Singh Sharma from the same institute, and for the first part, we have collaborated with Professor Justin Strong from NTU, and of course, we acknowledge our crystal growers and some other students who are involved in this work, and of course, the funding agencies which make the work possible. Okay, so why is fuel graphene an exciting platform to study quantum Hall effect? To answer this question, if we see that this is the band structure of ABC stacked fuel graphene, where you see that the band structure really changes quite a lot if you change the number of layers. So the band structure is really tunable with number and stacking of layers. And there have been studies, for example, from Pablo's group, where you study that they have studied the Landau level crossing that occurs as a function of magnetic field. And this is some different study of, again, Landau level crossings from Professor Jeannie Lau's group. And again, another new study from Pablo's group, where they have studied the Landau level crossings as a function of electric field. And from our own group, we have reported before the effect of strong electronic interaction in this system and how they reflect in the corresponding quantum Hall ferromagnetic states. In this talk, I want to cover three slightly different aspects. The first part is I'm going to focus on Betti phase in ABA trilayer graphene and the integracy of it. And in the second part, we are going to play with trigonal warping of a band that is there in the low energy bands of fuel graphene. And in the third part, I'm going to study how studying different Landau level crossings, you can actually determine the Landau level sequence in this system. Let me start with the first part, and here is the main result. So at the end of the talk, hopefully I'll convince you that the Shubnikov-de phase and frequency of a particular band in terms of a magnetic field can get affected by a coexisting band. And by exploiting this fact, one can actually determine the Betti's phase of one band using the SDH oscillations of another band. So I'll keep it short, and for more details, please refer to our archive version of the paper. Okay, so let me start with the ABA trilayer graphene basics. So ABA trilayer graphene consists of 3 layers of carbon planes, where the second layer sits on top of the first layer, but this is offset by one carbon-carbon atomic bond, and the third layer is directly sits on top of the first layer. And if you see the low energy band structure, you will see that there are 6 bands, 3 conduction and 3 valence bands. And if you zoom in near one of the valleys, you will see that there is a pair of linear band and there is a pair of quadratic band. However, there are another 2 quadratic bands which are gapped out at an energy scale irrelevant to the transport studies. And so in a single band system, there have been studies of Betti's phase, and in graphene it was first reported by Philip Kim's group. However, in fuel graphene there are still some confusions, and I'm going to focus on how you can extract and what is the possible precautions to study Betti phase in the system. Now, what is unique about this system is, if you see the low energy band structure, you have this linear band which look like monolayer graphene like band, so we'll refer to as monolayer band. And similarly, you have this quadratic band which looks like bilayer graphene like band, so we'll call it bilayer band. So this is the simplest system which provides you both massless and massive carriers at the Fermi energy. And also, since the Betti phase depends on the dispersion of the band, so you have both trivial and non-trivial Betti phase carriers at the same time. So as a function of energy, we can calculate the Betti phase of both the bands individually. And what we see is, as expected, if you have a linear band, the Betti phase is pi, and it decreases to 0 only when the Fermi level comes really close to the band gap, monolayer band gap. And similarly for the bilayer band, the Berry phase has a almost constant value of 2 pi, and it decreases to 0 when the Fermi energy comes close to the bilayer band. And to study magnetotransport and quantum Hall, we follow the same strategy where we sandwich the ABA trilayer graphene in between two hexagonal boron nitride flakes. And in these devices have very high mobility, exceeding 500,000 centimeter square volt in per second inverse, and very high mean path, which makes this study possible. Here is our main data, where we plot the conductance of the system as a function of magnetic field and density. So each of these dark lines are lines of constant filling factor, and what we see is we see this additional feature on the electron side at around 10 volt, and when we plot the band structure in the same energy range, we will see that this additional feature is aligned with the Dirac band gap. And we can calculate the Landau level spectrum in this system. We see two kinds of Landau levels. The red Landau levels come from the linear band, and the green Landau levels come from the bilayer band. And we see that this n equals to 0 Landau level of the linear band is special because it does not depend on the magnetic field. So it crosses with several bilayer-like Landau levels. And hence, comparing this diagram with the experimental data, this additional feature at around 10 volt can be identified as the Landau level series of Landau level crossings due to the 0th Landau level. And when we take a line slice at a particular density, we see two frequencies in the resistance. The low frequency sparse oscillation that you see at low magnetic field regime that occurs from the linear band, and this high frequency oscillation that you see here that occurs from the bilayer-like band. But here is the main result of our study. So since the frequencies of the monolayer oscillation and the bilayer oscillations are different, by looking at frequency you can isolate the monolayer-like Landau levels and bilayer-like Landau levels. So I'm going to show you three representative slices of bilayer-like oscillation. So here is the first slice where the Fermi energy lies in the Dirac-like conduction band. And here is the second slice where the Fermi energy lies right at the Dirac band gap. And here is the third slice where the Fermi level lies at the Dirac-like valence band. Now the point to notice is here is the first and third oscillations, they are in phase. However, when the Fermi level sits right at the Dirac gap, the phase is exactly pi shifted. Now we have already seen the calculated Berry phase in this energy range for the bilayer band. And for the bilayer band, we have seen that the Berry phase is almost constant 2 pi. So this changing phase is not definitely the Berry phase of the bilayer. So in what follows, we'll try to understand what is the source of this additional phase change. Okay, so not only the phase change, we can calculate the phase of each of these oscillations from the Landau level index plot, and looking at the intercept, we can tell that the phase of these oscillations are minus pi, 0 and pi respectively. And not only these three representative slices, we can slice at any arbitrary densities, and we see that all the line sizes provide only minus half or half intercept, depending on the Fermi energy in the conduction band or in the valence band. And surprisingly, only when we tune the Fermi level right across the Dirac band gap, we see that the intercept takes continuous values, and hence the phase changes continuously. Now, none of this observation can be understood if we assume that the Berry phase of the bilayer band is insensitive to the monolayer band. So how do we understand this? So we note that the semi-classical conductance contribution due to a band can be modeled as a cosine function where the frequency depends on the Fermi surface area, and the phase depends on the details of the band structure because it encodes the Berry phase. Now here in ABA trilayer graphene, since you have two bands, so in general you will need two cosine terms with two different frequencies and two different phases. Now if we constrain ourselves in the shaded region, we note that due to the large Landau level gap from the linear band, the conduction is dominated by the bilayer-like Landau levels, and hence you can throw out the first term, and we note that the frequency of the bilayer-like oscillation is given by the density of the bilayer band. But here is the key point. When we do these measurements, we do at a constant gate voltage. And the constant gate voltage sets only the total density of the system. And when you change the magnetic field at a constant gate voltage, the density between the two bands can oscillate as a function of magnetic field. Second point, we cannot experimentally maintain a constant Fermi energy. Experimentally, what we can do is a constant density. So we are not taking a constant slice in this diagram. However, we are maintaining a constant density. So we change the bilayer density by the total density, and in doing that, we find a new frequency term now, which relates to the total density of the system instead of the bilayer density, and a new phase, which apart from the and the new phase of the bilayer-like oscillation, which apart from the bilayer Berry phase, also depends on the filling factor of the monolayer band. Now, with this, let's look at some special cases. For example, in the blue shaded region, we note that when the Fermi energy lies in this shaded region, the monolayer filling factor is just constant, -2, because of this large Landau level gap. And this shifts the phase of the SDH of the bilayer SDH oscillations by -pi. Now, this is slightly non-trivial because we just saw that the presence of a linear band can shift the phase of a trivial band by a non-trivial amount. And we also note that this additional phase shift comes because of this filling of the n equals to 0 Landau level. And we all know that the presence of the n equals to 0 Landau level is a direct consequence of pi Berry phase of a linear band. So in other words, the phase shift that we see in the bilayer band is directly the Berry phase of the monolayer band. And now if we constrain ourselves in between the two monolayer Landau levels, we see that the monolayer filling factor is 0, and hence the bilayer oscillations does not show any additional phase shift. And on the right hand side, the monolayer filling factor is 2, and that is why the phase gets shifted by +pi. Now, this explains the data that we have presented before. But not only that, there is an important consistency check. This equation tells us not only does the phase gets modified, the frequency gets modified as well. And in a single band system, you expect that the frequency is given by the density or the Fermi surface area. However, this equation tells you that the frequency of the oscillation is given by the total density of the system, or the total Fermi surface area, monolayer plus bilayer. And experimentally, you can find out the frequency from a Landau level index plot. The slope of this curve is going to give you the frequency of the oscillation. So to experimentally verify this, let's follow at a constant filling factor, which is directly related by the corresponding Hall conductance measurement. And we know that at this regime, the monolayer filling factor is 2, so we know the bilayer filling factor also, which is 26 minus 2 is 24. And since we know the filling factor of both the bands individually, we can calculate the density of both the bands and sum them up to get the total density at all these gate voltages. Now, at each of these gate voltages, we have also done the Landau level index fitting, and from the slope of the curve, you will get a density, and we plot the same density. We plot the density on the same curve, and we notice that for all the gate voltages, the density that you get from the Landau level index fitting precisely matches the total quantum Hall density, and which directly verifies this equation. But this is again surprising, because naively you would expect that the SDH frequency would tell us band specific property, the Fermi surface area of that particular band. However, here we are getting total density and hence the total Fermi surface area. Yeah, so that brings me to the summary of the first part. We have shown that in a multiband system, you can have this additional filling enforced phase shift due to the presence of another band. And we note that finding Berry phase from the intercept of this Landau level index plot and the Fermi surface area from the slope of the Landau level index plot is the de facto method in the community. However, we have just shown that in multiband system, when I have to calculate Berry phase and the Fermi surface area, additional care must be taken. And Lastly, we show the extracted bilayer phase as a function of gate voltage continuously across the Dirac band gap. And in this panel, what you see is theoretically calculated Berry phase of the monolayer band across the Dirac band gap. And you see that the experimental data closely follows the trend. This further verifies that the Berry phase of the monolayer band indeed gets reflected on the bilayer band oscillation. With this, I finished the first part, and I'm going to change gear a little bit, and I'm going to focus on now how trigonal warping of a band can actually change the interaction between different Landau levels in this system. Okay, so we study ABA trilayer graphene, and this is a unit cell of ABA trilayer graphene. There are these 3 layers, and we particularly highlight a hopping parameter, which is gamma 3, which connects to A1 to B2 and A3 to B2 atoms. And to see the symmetry of this hopping parameter, let's take a top view of the crystal structure. And here is the gamma 3 hopping parameter in this picture. And as you can see that there are 3 pairs of blue atoms around a red atom. That means that gamma 3 has the same triangular lattice symmetry. And if you see the band structure, you see the monolayer bands, their wave functions actually lie on the A1, A3 and B1, B3 atoms. And for the bilayer band, the wave function lies on A1, A3 and B2 atoms. And we note that gamma 3 is precisely the parameter which connects this A1, A3 and B2 atoms. That means that gamma 3 will control the trigonal warping of the bilayer graphene-like band. And theoretically, it's also easy to check. In the calculation, if we set a non-zero gamma 3, we see that the Fermi surface of the bilayer band is strongly trigonally warped. However, the Fermi surface of the bilayer band becomes a circle if we set gamma 3 equals to 0. Now, experimentally, what do we measure? We measure the conductance of the system at a particular magnetic field as a function of electric field and density. And the density axis has been converted into a filling factor axis here. Now, each of these straight lines is a line of constant filling factor. And what we see here is this: we see these additional red blobs. These red blobs are actually Landau level crossings, and this becomes clear when you see some theoretical simulations. Here what we have done is we have calculated the Landau level energy as a function of electric field. And you see that there are a couple of Landau levels which are very sensitive to electric field, and they cross several Landau levels. And at the crossing point, you have more density of states. And that is why you see this more conductance, and this is the calculated density of state from the same Landau level diagram. And you see, whereas there are mostly there are crossings, there is a particular location where you see an anti-crossing here and here, and this also shows up in the Dawes diagram. And this calculated density of state can be directly compared to the experimentally measured conductance diagram. And upon comparing, you can directly find out this presence of anti-crossing here at this electric field. Now the question is, what has trigonal warping something to do with the anti-crossing that we observe in experiment? And that becomes very clear when you see the bilayer-like Hamiltonian and its wave function. And here is the trigonal warping term. And you see when the trigonal warping term acts on the bilayer graphene-like wave function, it generates a coupling between n and n plus 3 Landau level index. So in general, the presence of trigonal warping couples 2 Landau level with indices n and n plus alpha, where alpha is any multiple of 3. And in our case, we have seen the anti-crossing between 0 and 6 Landau level here. And surely enough, when you set gamma 3 equals to 0 in calculation, you see that this anti-crossing goes away. So this is a smoking gun evidence of the trigonal warping of low energy band, and yeah, and that's what we have shown by measuring this Landau level anti-crossing. Okay, so now I'm going to move to the third part, where we'll study the Landau level crossings as a function of electric field and magnetic field, and determine the Landau level sequence in this system. But before we do that, I have to introduce 2 more parameters, which are delta 1 and delta 2. So when you apply an external electric field, different layers of trilayer graphene, they do not sit at the same potential. So the delta 1 is the part of delta 1 is the part which takes care of the linear part of the electric field in between layers, and delta 2 is the part which takes care of the nonlinear part of the electric field. And here is the calculated Landau level energy diagram as a function of magnetic field, and we focus on this 8 zeroth Landau level from the bilayer band. So what we see is the zeroth Landau levels, they have competing symmetries and their energies are very close, and it turns out that delta 2 has a very important role to play to determine their sequence. And why is it important? There is a recent study by Jendra Jain's group where they have identified bilayer graphene and trilayer graphene as an interesting system to study non-abelian fractional quantum Hall effects. But what they need is they need the single particle Landau level ordering, which was not known in Debian trilayer graphene. So what we do is, so to begin with, we want to resolve the Landau levels. That is why we measure at high magnetic field 8 Tesla as a function of electric field and density, and each of these lines are constant filling factor lines, and the Landau level crossing shows up as a bright blob at each of these points. So what we see at nu equals to -2, nu equals to -3 and nu equals to -5, we see 1 Landau level crossings. However, at filling factor -4, we see 2 Landau level crossings. And we increase the magnetic field to 14 Tesla, we see that these crossings change their position a little bit. However, the crossings at nu equals to -2, it goes away. Now the question is, what does, again, delta 2 has something to do with the Landau level crossings that we do, and to appreciate it, we show a small simulation where we focus on these 2 Landau levels, zeroth Landau levels from the bilayer band, and see their valley separation. So it turns out that their valley separation is a strong function of delta 2, it comes with a 3p factor. So in simulation we are going to increase the delta 2, and you will see that this pair of Landau levels will come forward and will generate new crossing. So for example, at this delta 2, you have 1, 2, 3, 4, 5, 6 crossings. Now we can do this exercise at both 8 Tesla and 14 Tesla and match the experimental crossings, and we found out that delta 2 should have a value of 4.3 MeV. Now with this 4.3 MeV, we can calculate the Landau level energy as a function of magnetic field, and then we turn on the electric field, we see that it generates the same set of crossings that we have found in experiment at 8 Tesla, and similarly for 14 Tesla. So we get the same set of Landau level crossings. Yeah, so that brings me to the conclusion of this part. We have shown that, electric field is a very useful knob to study the interplay between Landau levels and its own another degree of freedom, which is trigonal warping. We have also shown that how studying different Landau level crossings, one can determine the non-uniformity of the electric field, which is quantified by delta 2, and by quantifying delta 2, one can actually determine the Landau level ordering in this system, and also the single particle Landau level orderings are important to understand further fractional quantum Hall data in this system. Yeah, so I have skipped some details. For more details, please follow our published version of the paper, and yeah, I'm probably ahead of time. Thank you for your attention.